The area between the parabolas with equations y equals x squared plus 2x plus a and y equals a minus x squared equals 9. What are the possible values of a? 1, negative 3 and 3, negative 3, negative 1 and 1, 1 and 3. So what we're dealing with here, we have a positive quadratic, positive in that the x squared has a coefficient of positive 1. And likewise here we have a negative quadratic, negative in that the coefficient of the x squared is negative 1. So positive quadratics, they always do this kind of thing, right? They always have kind of a positive smiley face and some minimum point, which we call the vertex, and maybe some roots. If it passes through the x-axis like that, it's going to have some roots right there and right there. So and negative quadratics, well, they're always like an unsmiley face, right? They look a bit like this, right? They're kind of going down. They have a maximum point right here. Again, we call that the vertex, and then two roots. These are called the roots right here. Maybe one root and maybe 0 roots. It depends on the quadratic you're dealing with, right? So if you're dealing with a negative quadratic, you could have just one root like that, and that's called a repeated root, or maybe no roots at all. That'd be that situation there. So you have to bear these things in mind when you're thinking about this question. So it's going to be very useful to get, if we can, the roots and the vertex of both of these quadratics, and then we can compare and contrast how they look on the same graph. So the first equation here is the x squared plus the 2ax and then plus the a. All right. Now to get the vertex, there are different ways of doing it. One way is to differentiate and then set to 0, because the vertex is ultimately a turning point. And to find the turning point, well, you set the gradient to 0 and solve, and that tells you the x value. But there is another way, and it's called completing the square. And that basically involves this process. So when you have an x squared, in addition with some coefficient, let's call it 2a, lots of the x, you can always write it in this form. You can always do x plus the a, and then square that, and then you have to minus the a squared coming out. So that's called completing the square. That's the way I often remember it anyway. And you can double check this by expanding the double bracket here if you want. It's called completing the square because, well, if you add the a squared over there, you get x plus a all squared, which is like a whole square, right? But this is how I'm going to use it. The x squared plus 2ax equals x plus a squared, and then minus the a squared. And you can apply that to, the first two terms here, right? This term and this term. We can complete the square on those two terms, as it were. And that's going to become the x plus, so you do half of the 2a is a, and then you square like that. And then you minus the a squared, so that comes out the back as a minus a squared. And we also have the plus a here as well. Now, I'm just going to factorize the constant term on the end there. So this, I'm going to write it like this. I'm going to write it as plus, and then I'm going to factorize the a, and then 1 minus the a, right? So I often refer to this as completed the square form because it tells you immediately where the vertex is. If you take a look at the dependence on x for this expression, you can see how we have x plus a and then squared and then plus some constant term here where a is some arbitrary constant. And therefore the absolute minimum of this expression is just going to be equal to this constant itself, this a times the 1 minus a. And that's going to occur when this first term goes to 0, and this first term goes to 0 when the x equals the negative a. So that gives you the x coordinate of the vertex, and the y coordinate is given as just this constant, the a times the 1 minus a. So if you can get it in completed the square form, it tells you the location of the vertex straight away. And for the positive quadratic here, that's going to be located at the negative a and the a times the 1 minus a. Okay, so that's a good thing to do. That is the vertex of the positive quadratic. All right, what else could we do? We can, I suppose we could find the roots perhaps of this quadratic. That's not difficult to do. If you want to find the roots, well, again, completing the square form is quite useful because finding the roots ultimately amounts to solving the quadratic to 0, because the roots are just where the x values go to 0. So what do? You can take your y value and set it to 0 and then solve for the x value. And in this case, that's going to be, to do it, you're going to minus that constant over there, and then you're going to square root to get rid of the square. So we are going to get the the a times the a minus 1, because I minused it over the other side, and then square root, and don't forget to do the plus and minus square root in that fashion, and then I would minus the a there, and that's going to give me the location of the roots for that particular quadratic. So that's the roots there, right? That's the roots of the positive quadratic. So let's take a look at the negative quadratic. The negative quadratic is the a minus x squared, and maybe for this one the best approach would be to factorize it, because it looks almost like something squared minus something squared, and we can use the difference of two squares yet again to factorize that quadratic. So the difference of two squares is this, right? A squared minus the b squared is the a plus b times with the a minus b. And basically, whenever you have one thing squared minus another thing squared, you can always factorize it in this form. This is called the difference of two squares, because it's one thing squared minus another thing squared. And we can apply that here. I know the a here is not squared per se, but you can write it as the root of a and then squared, right? There we go. Now it's one thing squared minus another thing squared. And we can factorize it in exactly the same way. So it's going to be the root a and then plus the x, and then the root a and then the minus the x. And the reason I'm doing this is because it tells me where the roots of that quadratic are, right? So the y value is going to go to 0 when any one of these factors goes to 0. The first factor goes to 0 when the x is negative root a, and the second factor goes to 0 when the x is the positive root a. So this quadratic is going to 0 at negative root a and positive root a. And moreover, it's pretty easy to see where the vertex of this is, because, well, it's a negative quadratic and it's the a minus the x squared. What does negative x squared look like? It's just the x squared graph turned upside down. So here's the positive x squared, vertex at 0, like that. Here's the negative x squared, vertex again at 0, like that. And if you add a to that, well, it's just the same as shifting the whole graph up by a. So you get something that looks a bit like this, right? That's the a. A would be right there, and this would be the a minus the x squared. And right here we'd have the negative root a, and then the positive root a, right? So these are going to be the roots, right? The negative root a and positive root a, those are my roots right there. And this coordinate here, this guy here, that is my vertex on that quadratic. So let's go ahead and draw both those quadratics on the same graph, and then we can compare and contrast between them. Let's start with the a minus x squared, because that one's nice and easy, right? It just has a, well, in particular when the a value is greater than 0, that's going to be a key consideration here. The a minus the x squared is going to be looking, a bit like this, right? So just the same thing again. It's going to be passing at the a right here, scooting down, passing through the positive root a there, and then passing through the negative root a right here. So that is the negative quadratic. What about the positive quadratic? What did we learn about that? Well, we figured out its vertex and the roots as well. That was this one right here. So the vertex is at the negative a times the, along with the a times 1 minus a. Let's write that down again. So negative a times with the a, and then the 1 minus a. That is the location of the vertex for that quadratic. Vertex, okay. And the roots were just that thing rearranged. So the negative a plus minus the root of a times a minus 1, right? So negative a plus minus the roots of a, the a times the a minus 1. Okay. So at the moment, I'm considering this graph where the a is greater than 0, and you can see for where the location of the vertex is concerned, that's going to leave us within the negative x domain. If a was positive, the x value here would be negative, and the vertex would be on the left half of this graph. But the y value here, if you take a look at it, we have a and then times by 1 minus a. Now the a would definitely be positive, but this 1 minus a, that could be positive or negative at the moment, because I'm just setting a greater than 0. Okay, so whether the vertex lies above or below the x-axis is going to depend on the sign of this term here, the a times the 1 minus a. So let's just investigate that, the a times the 1 minus a. Well, this 1 minus a, that's going to depend on, well, the sign of that changes, right? So if you set that greater than 0, then that means the a would be less than 1. So if the a was less than 1 but greater than 0, then that would leave the a here greater than 0 as well. So if a is between 0 and 1, this is going to be a positive times by a positive, and that would leave us with a positive y value for the vertex. But if the a was greater than the 1, then that would leave us with 1 minus a being negative, and the a itself would be positive. So that would leave us with a negative y value for the vertex. And moreover, if the a was less than 0, well, this first term would be negative, and this second term would definitely be positive. So again, that's going to give us a negative vertex, right? So the y value of the vertex would be negative. So this is where the vertex is going to lie below the x-axis. So vertex is below the x-axis, and in this situation, it's going to be above this one right here. So I need to make some further considerations with the a when I come to draw this. So as a first step at drawing this positive quadratic, I'm going to make the additional constraint that the a is less than 1. Right? So if the a is less than 1 but greater than the 0, then this vertex here is going to have an x value which is negative, but it's going to have a y value which is positive. Now there's some further insight to be gauged here, in that you can see the x coordinate of the vertex on the positive quadratic, right? So this is the positive quadratic, and these are the features of it. Right? We have the vertex, and we have the roots right here as well. Okay, so that's features of the positive quadratic. But for the negative quadratic, this guy right here, if you plug in the x value of negative a, let's go ahead and do that. So if you plug in the x value of negative a, you get a minus and then negative a squared. But negative a squared is just the same as positive a squared, so it's a minus a squared, and that's just going to be, if you factorize the a there, you get the a times the 1 minus a, right? What have we realized? We've realized this coordinate here, which is the vertex of the positive quadratic, actually lies on this negative quadratic, and that's always going to happen irrespective of the value of a. And that's a really good insight to be made before we try and draw this positive quadratic. And moreover, the y-intercept of this positive quadratic is going to lie at a itself. That's this point, because when the x value goes to 0, you just get a, and that tells us where this positive quadratic cuts the y-axis. So those are two really useful insights to kind of gauge. The vertex lies on the green curve, and also the y-intercept itself lies on the green curve for the positive quadratic. So when a is between 1 and 0, is going to look a bit like this, right? It's going to have the vertex on the quadratic itself. Let's put it there, perhaps. And then it's going to be scooting up, and it's going to be passing through the y-intercept, and it's going to be intersecting the green curve again at that same point. So it's looking a bit like this, right? The x value here is just the negative a itself. The y value here, that is the a times the 1 minus a, and the y-intercept is a itself. Now this question is ultimately concerned with the area between these two parabolas, so it's focusing on this area here, which we are going to calculate at some point using integration. But it's important to recognize what you're dealing with, because there's going to be a point where the argument kind of breaks down in that, well, when you have the positive quadratic and the a is positive, that puts the vertex left. So that puts the vertex in the left half of the plane. And moreover, it puts the y-intercept of the green curve above the x-axis. But imagine what happens as a tends towards 0. Well, the green curve is going to move down because it's a above the x-axis. As a steadily decreases, the green curve is going to slowly move down, and the vertex here would move slowly inwards, but it would do so such that the vertex is always on the green curve and always passing through that point. And when you do get to a equals 0, the green curve, the vertex would be right here, and the blue curve, the vertex would be right here as well. So when a equals 0, the blue curve is going to be above the green curve. It's going to be looking a bit like this, and the green curve will be looking a bit like this. And then as a goes to negative, then the green curve moves further down, right? But the vertex, the blue curve, is always going to be on the green curve. So it's going to be, it'd be a bit like this, right? Now Desmos can do a much better job of illustrating that, and I have gone ahead and made a graph in advance of exactly what's going on. Here it is. So we have the f of x right here. Let me just change the color of that one. Actually, let me change that to blue. Right, there we go. Right. So this is my positive quadratic, and at the moment I got the a value as 2. Right, so that leaves me with the vertex below the x-axis. You can see as the a value goes to the 1, that the positive quadratic it hits the x-axis, and then between 0 and 1, the vertex is above the x-axis, and then as the a value goes down to 0 again, that's the consideration I was just talking about when the positive quadratic is above the negative quadratic. Okay, so these is a really insightful illustration to look at. We have the a minus x squared, so that's the negative quadratic. That winds up to 2 there. And ultimately, we're concerned with this green area here, right? The area between the two parabolas, this area. And that, to find the area between two parabolas, a quick way of doing it is just to do the parabola which is above minus the parabola which is below, and then integrate between the limits. And the limits are going to be where these two curves intersect. And that's always going to be the y-intercept, right? They're always going to intersect at that point. We proved that by considering the fact that the coordinate on this curve is always going to be 0a, right? And a coordinate on this curve is always going to be 0a. So that's the point where one point where they always intersect. But the other point where they always intersect is the vertex of the positive quadratic. So you can see as I shift the a value around, the vertex is always on the green curve, and then when the a goes negative, it kind of does that thing, right? And again, we're saying the area between the two curves is going to be 9. Now you can see how this is going to give us two possible values of a, right? There's going to be a positive value of a where the area is roughly 9, right? And then there's going to be a negative value of a where again the area is 9. So that's where we're going to get the two values of a for this question. And it took me a bit of playing around just to figure all this out before I even tried to do the integration. I like to see things before I try and find the answers, and here recognizing the degeneracy in the a was not obvious. You had to kind of recognize all these features. In particular, the vertex of the blue is always on the green, and moreover they always intersect at the y-intercept. Once you recognize that, and the fact that the vertex has a coordinate of negative a, then it becomes quite clear that there's going to be two possible values of a where the area is 9. So let's go ahead and find those values of a, right? You can see how the green curve is always going to be above the blue curve. So I'm always going to be doing the negative quadratic minus the positive quadratic. So here's how we set that up in the integral. We do the negative quadratic, which is the a minus the x squared. That's the curve which is above, and then we minus the curve which is below. The curve which is below is the x squared plus the 2ax, and then plus the a, and then close bracket. And we want to integrate that between the limits where those curves intersect with respect to x. Now that's where the things kind of break down a bit, because the limits are going to depend on whether the a is positive or negative. When the a is positive, the lower limit would be negative a itself. So you could put a negative a in there, and the upper limit would be just that point there. The y-intercept again would be 0. So that would be the 0. That's when the a is positive. But when the a is negative, the upper limit itself would be negative a, because this blue curve would be moved down to this situation right here. Let's just remind ourselves on the Desmos, that would be here the a is negative, and you can see how the upper limit itself is the negative a. That's the 1 in this case, the negative a. A itself is negative 1, negative a is 1, but the lower limit again would be that y-intercept. So you can see how, depending on whether a is negative or positive, the limits are going to flip around. And that gives me an ambiguity in the sign on the integral here. When you flip the limits around, it just negates the overall integral. So what I'm going to do, I'm just going to stick a plus minus in front just to account for that ambiguity. Because when you flip the limits around, you put 0 there and negative a there, but that just has the effect of negating the overall integral. So I'm going to account for that back just by putting a plus minus here, and then I'm going to go ahead and evaluate the integral, and I'm going to set it to 9 at some point as well. So let's go ahead and do that. So so you can see I have a here. That's going to cancel the a here. We have the negative x squared minus x. That's going to be negative 2x squared there. And then we have the minus 2ax here as well. Okay. It's going to be useful to factor out that negative 2. So let me just pull it out. So 2. And again, I can disregard the negative because it's plus minus here. I don't really care basically about the sign. So I'm just going to disregard that. Factor out the 2 there. That's going to be x squared plus ax. And the limits again would be the negative a and the 0 and then dx. Okay, keep going that. So x cubed on the 3 plus the ax squared on the 2, and then chuck in the limits. Don't forget the plus minus 2. Chuck in the limits of negative a and 0. And what does that give us? It gives us the negative a cubed, which is just negative a cubed on 3. Oh, I forgot the 0, didn't I? Well, actually, yeah. So when you plug in the 0, it just gives us 0 because 0 cubed is 0, x 0 squared is 0. That whole thing gives 0. And then when you go to plug in the lower limit, you're minusing that whole expression. But again, I don't care about the sign. It's positive and negative here. So I'm just going to put plus minus 2 again. And then I'm just going to chuck in the limit of negative a. So you get the negative a cubed, which is negative a all cubed divided by the 3. And then plus the a times negative a squared. Negative a squared is going to be just a squared times a. That gives you a cubed. So you get a cubed and then divided by the 2 there. Okay. And what does this leave us with? Well, you got the a cubed as a factor there. And then you got the half minus a third. What is a half minus a third? A half minus a third is, well, it's 3/6 minus 2/6, which is 1/6. 1/6 there. So that becomes 1/6 of a cubed. And then times by the 2 becomes 1/3 of the a cubed. So you get a cubed on the 3 1/3 plus minus, and don't forget we're setting this equal to 9 because that's what the question was saying. The area is 9, so we can equate that to 9, and then solve for the a, right? So you times it by the 3, you get the 27, and then you cube root, and it's going to be, well, the cube root of 27 is just 3 itself, but accounting for the plus minus I don't care about the sign. It's going to be positive or negative 3. So that is my final answer here. When the a is 3, we get an area of 9, and also when the a is negative 3, we get an area of 9. And we can see that on the graph again if we go ahead and put the a as 3 here. So when the a is positive, that vertex is actually has an x coordinate which is negative 3, and that area there would be 9. And I've actually set that up in the integral here, equals 9. And likewise, when the a is negative 3, that's this situation here. So see how the green curve is moving down? That's what I talked about. And that's the same area there. It's just the limits slip around. So the a is 3 or the a is negative 3.